Hey everyone, I'm Jeremy Blum, and on a very special holiday edition of my Arduino tutorial series, we're going to be making this. Today we're going to use these awesome individually dressable RGB LED strips and some simple audio processing to get them synced up to music so we can make an awesome holiday display. Guest hosting with me today I have my good friend Brian Schiffer, who is a fellow engineering ninja from Cornell University, where we both attend college. He is really awesome with electronics. You want to tell him a little bit about what you do?
Sure. So I work on brainwave monitors with a startup company called Zio.
It's really, really awesome stuff, and so he'll be helping us out with the tutorial today. We're going to be learning about using op amps to amplify audio signals as well as filtering those signals.
And then we're going to actually feed it into the Arduino and use the Arduino to take those signals and actually control the RGB pixels that we have here.
It should be a lot of fun, pretty straightforward project, and you can use it to impress all of your friends during the holiday season. So let's get started.
Okay. This is the circuit we're going to be using. We're going to have to build this twice, one for the left channel and one for the right channel. So we start off with the weak input signal from the audio jack. Then we put this through an amplifier stage right here, and then we put it through a buffer, which finally feeds that into a low-pass filter stage here. So now I'm going to go through each stage individually and better explain them. So first we start here at the input. The input has a very weak signal based around 0 volts. So the signal itself goes both positive and negative with a small amplitude, VA. So this then is fed through a non-inverting op amp, which is governed by a set of equations which I'll specify from here at 1. So the first is the gain equation, which basically means that the voltage output, VB, from right here, is equal to VA times 1 plus R2 over R1. So in this case, we went ahead and made R2 a variable potentiometer so that we could actually change the gain to exactly what we wanted. And we set R1 to be a set constant of 100 ohms. So specifically what this means is that if, for instance, we had R2, our potentiometer, set equal to 0, we would actually get no gain, and it would just be VB is equal to VA. On the other hand, if we turned it all the way up to our max, which is 10K, R2 is equal to 10K, we wind up with VB equals to 10K over 100, so that's 100, plus the 1, so that's 101 VA. So one thing important to note here is just because this claims that it has 101 gain does not mean you could feed in a small voltage of maybe 1 volt and get 100 volts out, because the op amp itself has a positive high volt rail and a negative rail of ground, which this means that basically if it tries to amplify up to 100 volts, it'll only actually reach 5 volts. At the same time, if it tries to go negative, it's only going to amplify down to ground, which brings us to the next node, node B. So at node B, first of all, we get a gain as shown here, so we get a larger signal, and also as mentioned earlier, the negative signal will actually hit the ground rail, so we won't actually see that. What this is called is a half-wave rectifier. So whereas before we could see that it went positive and then negative, at negative it'll instead just stay at ground. So this way we only see a gain from VA up to VB for only the positive voltages. This is governed by the clipping from the op amp. So then from here we actually feed this into what's called a buffer. So the buffer basically directly feeds the output signal back into the negative rail. So this causes it to just have a gain of 1. So the reason why this is useful is because it helps us separate our gain stage over here from our filtering stage over here. So this makes sure that our gain doesn't affect the filter in any way except providing the initial signal, and also that the filter can't discharge back through the gain stage. So this brings us to the last node, our output node C, which will eventually be fed into our ADC of the Arduino. So at this point, what we are doing is we're using what's called a low-pass filter here. So this uses a capacitor and a resistor in parallel in order to try to make sure that this voltage doesn't actually go all the way down. This allows us to only look at kind of the overall average of the amplitude. So this graph looks like this. So we have our initial curves from over here in B, and now instead of going all the way down to ground, we instead have charged up our capacitor here, which will then start discharging across the resistor over here. So we'll charge up the capacitor, and then the capacitor will start discharging until we begin going back up and the voltage has exceeded the voltage of the capacitance, which will then have it go back up, and so on. So this allows us to have a smaller ripple and actually kind of get an average of the entire signal. This is governed by something called tau, which is basically just the resistance times the capacitance. So in this case, tau is equal to RC. And here we're using a 10K resistor and a 10 microfarad capacitor, which results in tau being 1/10 seconds. So from here we can now take this filtered signal and feed it into our ADC, or for testing we also had an LED hooked up to it that would just directly illuminate based upon if the magnitude was high enough to provide voltage to this LED.
Now that Brian's shown you a general schematic of how the amplifier works, let's go ahead and take a look at an overview of the entire system and figure out our power requirements. We know that in each of our 50 pixels, we're going to have a total of 3 separate LEDs, a red, a green, and a blue LED. Now each of these LEDs has an approximate current going through it of about 20 milliamps based on the current limiting resistors that are in the pixels. But we have 3 of them, so the total output, or the total current requirements of each individual pixel, since these are in parallel, are going to be 60 milliamps per pixel, with 20 milliamps per LED. But we have 50 pixels total, so we're going to have 60 milliamps times 50 pixels, which is going to give us 3 amps of current consumption at 5 volts. That's quite a bit of power. We definitely can't power this off the Arduino directly, so we're going to need an external power source. In our case, we used an old computer power supply, which we'll show you in just a minute. But you can also get wall warts, like I've used in previous videos, that can supply up to 3 amps at 5 volts. So make sure you get an appropriate power system for the LED setup that you have. Now that we know that, we can kind of draw an overall system schematic for how we're going to wire everything together. We're going to have wall power at 120 volts like we always do. That'll go through some form of power supply. In our case, like I mentioned, it's an old computer power supply, but in your case it might be a wall wart. And then we'll have the lights hooked up to the power supply and to our Arduino. So imagine this is our long strip of lights and they're all connected together. There's going to be a couple of important things here. We're going to have a 5 volt signal, or a 5 volt power rail that's going to connect to the power supply here. And then of course there's also going to be a ground. Keeping in mind that you always have to connect the ground signals together in your entire system so that everything has the same reference point. So those will be connected like so, but then we'll also have the Arduino. So if we have the Arduino down over here, there's 2 wires that are going to have to connect from the Arduino to the lights. So the lights have a total of 4 wires that come out of them. There's the power and ground wires, and then there's a clock and a data line. So both those will have to go to arbitrary pins on the Arduino that we can choose. I specified pins 3 and 2 in my code, but you can choose whatever you want. So pin 3 will be the data line, and pin 2 will be the clock line. Okay, and now let's not forget to make sure that we connect our grounds together. So ensure that the ground is connected to the lights, the Arduino, and your 120 volt wall power. So here's our ground right here. Now also going into the Arduino, we're going to need to have the analog inputs from the rest of our system. So the amplifier that Brian just showed to us is down over here, this amplifier circuit, which I'll show you on a breadboard momentarily. And there's going to be 2 outputs from that, the left and right amplified signals. So those will both feed into analog inputs on our Arduino. I chose A0 and A1. And this is going to be getting its original signal from some kind of stereo. So if you have a stereo system over here, what you will probably want to do is use a headphone splitter. Have one of the wires go to speakers so you can actually hear what's playing. And have the other splitter feed into the amplifier circuit that we just developed. And so there's going to actually be a total of 3 wires that you need here. Because it's a stereo signal, there'll be left and right, but each left and right wire that you cut out will have a ground signal too. You only need to keep one of them, but make sure you connect the grounds in. So there'll be a ground, a left, and a right. And I'll show you how that gets hooked into the system in just a second. So this is our overall system schematic here. And let's go ahead and get it wired up in the real world and start playing with it.
So here we have the modified computer power supply we're using to provide power just to the lights. So in order to get one of these power supplies working, you have to connect the switch line that normally tells it when to power on directly to ground to make sure that it constantly stays on. So here we can actually see the 4 lines coming from our strip of LEDs. We have power and ground, which go directly to the power supply. We also have the ground from the power supply broken out so that we have a shared ground that's shared between the LEDs and also between the Arduino. And then in addition, we have these lines right here coming from the LEDs, which is our data and our clock, which is then fed to the Arduino, which Jeremy will now talk about.
Okay, so here we have the circuit all wired up, just like Brian showed in the schematic earlier. First and most important thing, we have our audio signal coming in at the top here. Basically, we've taken apart a pair of old headphones and used 2 wires to bring them in here. So each wire from the headphones, the left and right headphones, has a channel and a ground. So you need to bring in both in channels and just one of the grounds and make sure you hook it up into the ground of the rest of your system. And don't forget, I know this looks complicated, but you'll be able to download the full schematic and breadboard view from my website. The link is in the description. Here we have the quad operational amplifier that we're using. So there's 4 op amps in here. The 2 on the left are the gain op amp and the buffer op amp for the left channel, and the 2 on the right are the gain and buffer op amp for the right channel. Down here we have our 2 potentiometers, which are used to adjust the gain on each signal so that we can get it just where we want it. And we have LEDs that indicate the approximate amplitude level of each stereo signal. Along with those, we have the resistors and our capacitors for our RC circuit, which remember is doing a low-pass filter that allows us to get the overall amplitude of the system without worrying about the particular frequency of the notes. So that's really useful for feeding it into the analog to digital converter of our Arduino, which is then happening with these 2 wires right here. They feed into analog pins 0 and 1 on the Arduino. Let's not forget that this system has to have 5-volt power, although it's not necessary to power it with the large, bulky computer power supply that we're using for the LEDs though. So we're hooking it up to the 5-volt and ground from the Arduino so that the op amp has the power it needs to do all the amplification. And then the last thing here is don't forget to hook up the signal and clock lines from our LED strip that we showed earlier. Okay, now before you do any programming on your Arduino at all, you should be able to confirm that your amplifier circuit is working correctly. Right now, the only thing we're actually using the Arduino for is power and ground. Basically, it's just a power regulator at this point. So we're feeding in the power and ground there, and we have our headphones feeding into the amplifier system. And we can see that with the music playing in the background, which you guys can hear, that the LEDs are blinking in accordance with the current amplitude of the music that we're listening to, which is awesome. And don't forget to check that your pots work. You're going to want to tune these LEDs so that they're blinking at the appropriate brightness based on the amount of music. So if I turn this down, you can see that the green LED blinks less and less. So we want to tune it to an appropriate value where we're getting a good amount of brightness where you'd expect the peaks to be. And once at that value, that's perfect, and we can feed into the Arduino, do some awesome programming, and make it control the whole LED strip, and it's going to be really great. Now that we have our circuit set up, it's time to run our first simple program. There's a few things you should make sure you take care of before you start to write the program now. The first thing is, since my last Arduino tutorial, Arduino has released version 1.0, so make sure you have the newest version of their programming environment. You can get it from arduino.cc, click on download, and then make sure you get the newest version of the programming environment. It changes the extension name of the file, so you won't be able to open the files I'm uploading unless you have the newest version. The next thing you'll need is to navigate to Adafruit's GitHub repository for their RGB LED driver library. So if you go there, you'll be able to see their GitHub repository, click on the zip file, download it, and put it in your library folder of your Arduino programming environment location, installation location, so that we can use their library. So big thanks to Adafruit for writing that library. It makes this whole thing quite a bit easier. Once you have those 2 things, you're ready to start writing your program. I've already written a bunch of it here, and then we'll fill in some of the important parts. You're going to need to include the SPI library because these lights use a modified version of the SPI interface, which we've talked about in previous videos. You'll also need to include the library that you downloaded from Adafruit's website. As usual, I've defined pretty names for our analog input pins and our light control pins so that we can reference them later in the program more easily. The inputs from the amplified audio signals are in analog input 0 and 1, and the light control pins are pins 3 and 2. The next thing you want to do is set up the library as per the instructions for how Adafruit developed it. Basically, the library is called WS2801 because that's the kind of control chip that the LEDs use. So of that object type, we're going to define something called a strip, which is the variable we'll use to refer to our particular strip throughout the rest of the program. There's 3 parameters that you set up. The first one is the number of lights in the strip. Ours has 50. And you also need to set the data and clock lines and where they're hooked up to. So we defined those as pins 3 and 2 earlier, so you plug those values in here. In setup, you want to set up a serial connection as we often do so that we can do some debugging in just a bit. And you also want to initialize the strip. Strip.begin initializes the strip. Strip.show sets up all the LEDs to start displaying their current values. Okay, now let's get into the good stuff. If you go into the loop, the first thing I've done here is put in some debugging information. Basically, you'll notice that these first 3 things are prints instead of print lines. Basically, that means that they're not going to the next line after they print out. So it'll print out an L, a colon. To the right of it, it'll print out the value for the left channel input, put some spaces, then put out the right channel output, or the right channel input. This will be really useful for identifying the range of values that we have to deal with so that we can more effectively tune our program to get the maximum range of amplitudes from the music. The next thing you want to do is go ahead and actually read one of the channels so that we can do some good audio processing on it and get it to control the lights. To start off, we'll just focus on the left channel. So we're going to do an analog read of the left channel, just like we did above. And remember, to do that, you do analog read and you put in the pin name. But we're going to want to map this value because it's going to come in as a value between 0 and 1023. But in reality, we're only going to want a hue that ranges from 0 to 255, and I'll explain that in just a bit. But basically, our colors that we send to each LED will be a number from 0 to 255 that represents the RGB color that you'll be seeing on the LED. So the first thing we'll do is a map here. We'll map the analog read. I'm going to start by guessing that it's going to be around 400 or 500. Since I've already tested this out, I can tell you it's a pretty good guess. But basically what's going to happen is we're not going to hit the full range of the analog to digital input. It's generally around 0 to 400 depending on where you have your potentiometer set. But we'll play with this in just a bit, and you can kind of experiment with this value. But regardless, it'll take the number from 0 to 400 and convert it to a number from 0 to 255 by doing a linear conversion. The next thing, as I've mentioned in the past, you'll almost always want to use a constrain function when you do a map function, because this does do extrapolation. So if it does get a value above 400, say 410, it'll map it to a value above 255. But having a value above 255 is meaningless because hues can only range from 0 to 255. So let's constrain it to those values, 0 to 255. Okay, perfect. The last thing you should do is set this equal to a variable that we'll be able to use. I'm going to make it a byte called hue. The reason I'm doing a byte and not an integer is because it's only a number from 0 to 255. So we can save some space by calling it a byte, because 0 to 255 is 2 to the 8, or an 8-bit number, or a byte. Next up, we're going to use one of the Adafruit helper functions that she defined on her website, which is really helpful, as usual. So we're going to use that function to convert that hue, that value from 0 to 255, to a 24-bit color value that the LED strip will actually understand. So the value that we convert it to is called an unsigned integer, 32-bit unsigned integer. And this is, just like you would define something as an int, we're going to define something as a uint32t. And that's just an unsigned 32-bit integer. So we'll call that color. And we'll use the wheel function, which I'll show you in just a minute, to convert that from the hue. So if you scroll down, I've already copied some of Adafruit's helper function that they've put together for this particular RGB LED pixel strip. So the wheel function takes a byte of a hue that we defined earlier and outputs it to a 24-bit color value. You don't need to understand exactly how this works, but basically if you go on Google and type in color wheel, you'll quickly understand what it is and why it's doing the conversion it is. There's one other helper function that we'll be using called color, or that you can use, that will convert an RGB value to a 24-bit color. For right now, we're just going to use the hue functionality. Okay, so we have the color now. The next thing we're going to do is go through a for loop, go through each individual pixel, and set its color value based on the hue that we determined from reading our analog input. So basically, each amplitude is going to map to a different hue on each LED. So I've already set up our for loop. We're going up to the maximum number of pixels and setting a value at each one. So we'll do strip.set pixel color, and this is just a function that's defined in the library that we're using. So for I, which is the particular pixel that we're looking at right now, we'll set it to the value color that we had just defined earlier. Okay, so that's all set. The last thing we have to do now is tell it to show the strip, and we'll put in a delay between each run through the loop so that the lights don't update too quickly and make us nauseous. So now we'll upload that to the Arduino, and we'll take a look at the serial output and tune the system to make it look awesome. So we have our serial debugger running, and we have some music playing now, and we can see it's working quite nicely. And you can also use kind of tune these LEDs to adjust the rate with which the lights respond to the music. You can make them more or less sensitive by adjusting the potentiometer. So right now we only care about the left channel, which is the green one. So by adjusting the green potentiometer, you can see that we can change just what the threshold is for them to respond to the music. And you can see that if you look at the serial monitor, it changes the maximum minimum possible values for the serial input. So before we guessed that it would be from 0 to 400, but we can really see that it's going up to 600. So you might want to consider changing that. But depending on how you tune the potentiometer, you're going to get different values. So if I turn it down, now it's closer to 0 to 400, although it peaks above it sometimes. That has a pretty nice effect though, right there. So we'll leave the potentiometer at that value and leave the map from 0 to 400 like we had it before. And that looks pretty good. So I think now we're ready to take it to the next step. For the last step here, we're going to try to make this a lot cooler. What we'll do is we'll have a left and right half of the LED chain defined. The left 25 will correspond to the left audio channel and the right 25 to the right audio channel. What we'll do is we'll have on each sample the previous sample propagate away from the middle on the left and right side, and then we'll bring in a new sample into the middle. So what this will kind of result in is there'll be a delay effect as the music comes through each channel, and you'll be able to sort of see the music propagate through each channel as it goes from the middle of the chain to the end of the chain. This should be really cool. So to do this, we'll use two arrays of length 25. I've drawn them shorter here just to make it easier to draw. And what we'll do here is we'll use basically the same method for the left and right, and then swap one of them at the end so that we have them both propagating from the inside to the outside. What we'll do on each run through the loop, we'll move the previous instance one to the left from the end of the array. Well, the first one, the one that's at the beginning, will get discarded, and then we'll pop a new one onto the end. So this will be the most recent sample. And so this will happen on each go through the loop, and then we'll be able to use both of these, bring them into the final array that controls the entire LED strip, and use it to make a really neat propagation effect. So let's get this programmed real quick, and then we'll see it in action. In favor of saving some time here, I've gone ahead and already put the program together that will control this new array system that we're going to be using. Remember, you can download all this code on Element 14 and from my website or my GitHub account. Okay, so there's just a few things that kind of changed around here, so let's take a look at them. The first thing was I defined two new constants. Remember, we've done this before. Constant length 50, because that's the length of our LED strip, and half length, which is just length divided by 2, just because we use them in a bunch of places for the rest of the program, and it made everything easier. So I plugged in length here where we just had the length 50 before. The next thing you want to do is make sure that you instantiate two arrays, one for each half. These are just going to be length 25, so we define the length in here as 25, because half is 25. And remember, these are uint32_t's, because they're holding those color values that we talked about in the last programming run-through. I've gone ahead and removed all of our debugging serial stuff since we don't care about it anymore. We're just going to look at all the pretty colors. So you'll want to make sure on the setup that we fill in each array, the left and right array, with zeros so that we don't have garbage data that we end up propagating. And then you just start the strip like you did before. Both of these lines of code are exactly the same as they were before, except they now refer to hue left and color left, because we now have the same lines of code for hue right and color right. So these are just looking at the analog channels, getting a hue, and then converting that hue to a 24-bit color, which is stored in a UINT32T. Okay, the next thing we'll do, which we just talked about, is we have to shift the current values. So we're going to look through the entire half array, each of the two half arrays, and we'll look at the last value. We'll move it one to the left towards the beginning of the array, and we'll pop in a new value at the end. And we'll do this for both the left and right arrays. So what this is doing right here specifically is moving the previous value towards the front of the array. So this is what's doing our propagation here. After we've propagated, we now have an open spot at the end of the array at location half minus 1, right? Because length half is 25 and the array is 0 to 24, so half minus 1 is 24. So at position 24, we pop in our new color left and color right based on the current audio amplitudes. And at that point, our arrays are both filled and ready to go, and all we have to do is put them on the LED strip, and that's pretty straightforward. This for loop is just like it was before, except now it's half, because we only want to go from the middle to the end, but we're going to do it twice, one for left and one for right. So for the left one, it's very straightforward. You just go from 0 up to the half, and you just fill in the array based on the one we just made. The right one is a little bit more complicated because we need to flip it around first. So at each I from 0 to 24, what we're going to do is we'll look at length minus I minus 1, which basically allows us to propagate backwards through the array as we increment our index numbers. And that'll make the nice effect of it propagating from the inside to the outside. And that's basically it. Everything else is the same. We still have to show the strip afterwards, and then we add a delay. I changed the delay here to 30 from before just because I thought it looked nicer, but you can play with this value a lot. The sample rate will affect just how the strip looks. So now I'm going to go ahead and upload this to our Arduino, and we'll take a look at how awesome it is. So what I've done now is I've put together a quick little program on my computer in a programming language called Pure Data, which is a graphical programming language that simply outputs a frequency on my audio channels. So right now I have a frequency set, and I can crank up the amplitude a little bit, and sure enough you can actually see the sine wave propagating across the channel of LEDs. It's really cool. And as I increase or decrease the frequency, you can see we start to get an aliasing effect, and if I increase the frequency enough, it becomes a basically solid color. And then I can bring the frequency back down, and you start to be able to make out the wave again, all the way back down to a frequency of 0. And then adjusting the amplitude inevitably changes the hue and the color, and we get some really neat effects like that. And I can do the same thing with the right and left channels. But no one wants to listen to this crap all day, so let's go ahead and listen to some actual music. thanks for watching a very special holiday episode of my Arduino tutorial series. Don't worry, there are many more tutorials to come. I'm not going to stop making them. Thanks a lot for Brian Schiffer for helping out today. We had a great time.
Thanks for having me. It was awesome.
Okay, so yeah, definitely go check out my website, jeremyblum.com, or Element 14, or my GitHub page. I have all the source code, schematics, everything you need to put this project together up on there. It was a lot of fun. I really suggest you guys check it out. And there might be some bonus footage from this tutorial coming around the corner, so definitely keep your eyes peeled on my YouTube channel and on Element 14. I look forward to seeing you guys next time. Thanks a lot for watching.
Thanks.
Thanks to Element 14 for helping me to sponsor this video series. They were kind enough to provide a lot of the materials that I'll be using to create these tutorials. Feel free to go visit their website at element14.com. Check out their community, which is a great place to talk to people about electronics, the Arduino, and basically anything else engineering related. And they also have a store where you can buy a lot of the parts that we'll be using in these videos.